Welcome to our exploration of probability and statistics, the fundamental tools that help us navigate uncertainty in our data-driven world. Probability is the language of chance, providing us with a framework to quantify uncertainty in a precise mathematical way. It allows us to measure the likelihood of events, ranging from 0 for impossible outcomes to 1 for certain outcomes. With these tools, we can make rational decisions even when facing uncertainty. At its core, probability is calculated by dividing the number of favorable outcomes by the total number of possible outcomes. Statistics is the science of learning from data. It provides methods to collect, analyze, and interpret information, allowing us to extract meaningful patterns from seemingly chaotic numbers. Statistics is typically divided into two main branches. Descriptive statistics summarizes data using measures like mean and median, while inferential statistics allows us to draw conclusions about entire populations based on samples. Together, probability and statistics form a powerful toolkit for navigating our data-driven world. They transform uncertainty into informed decisions across countless domains. These tools enable effective risk assessment in finance, drive scientific discovery, inform business strategy, advance healthcare, and power artificial intelligence systems. The key takeaway is that probability and statistics provide the essential foundation for making sense of data and uncertainty in our modern world. In probability theory, we need to understand how to visualize and represent possible outcomes. The sample space is the set of all possible outcomes from a probability experiment. For example, when tossing two coins, the sample space consists of four possible outcomes: both heads, both tails, head then tail, or tail then head. An event is a specific outcome or a set of outcomes that we're interested in. Events are subsets of the sample space. We can visualize the relationship between events and sample spaces using Venn diagrams. Here, the entire rectangle represents the sample space, while the circles A and B represent different events. When working with events, we often use set operations to describe relationships between events. The top diagram shows the intersection of events A and B, outcomes that belong to both events. The middle shows their union, outcomes in either A or B. The bottom shows when one event is a subset of another. Let's consider a classic example, rolling a fair six-sided die. The sample space consists of 6 possible outcomes: 1, 2, 4, 5, and 6. An event could be rolling an even number, which includes the outcomes 2, 4, and 6. This event is a subset of our sample space. When we roll 2 dice, the sample space becomes more complex. We now have 36 possible combinations, as shown in this grid. Each cell represents one possible outcome. An example event might be rolling a sum of 7, which occurs in 6 different ways: 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, or 6 and 1. To summarize, the sample space contains all possible outcomes of an experiment. Events are specific outcomes or sets of outcomes we're interested in. Venn diagrams help us visualize relationships between events, and set operations allow us to define complex events. The addition rule is a fundamental concept in probability theory. This rule helps us calculate the probability of either one event or another event occurring. Events can be either mutually exclusive or non-mutually exclusive. Mutually exclusive events cannot occur at the same time. The addition rule is represented visually using Venn diagrams. For any two events A and B, the probability of A or B equals the probability of A plus the probability of B minus their intersection. The formula is P of A or B equals P of A plus P of B minus P of A and B. For mutually exclusive events, which cannot happen at the same time, there is no overlap between the events. Since there's no overlap between mutually exclusive events, their intersection is 0. So the formula simplifies to P of A or B equals P of A plus P of B. Let's consider an example with a bag of colored balls. Suppose we have a bag with 3 red balls, 2 blue balls, and 5 green balls. There are a total of 10 balls in the bag. The probability of drawing a red ball is 3 out of 10, or 0.3. The The probability of drawing a blue ball is 2 out of 10, or 0.2. Since drawing a red ball and drawing a blue ball are mutually exclusive events, we can use the addition rule. The probability of drawing either a red or blue ball is 0.3 plus 0.2, which equals 0.5. These events are mutually exclusive because we can't draw a ball that is both red and blue simultaneously. To summarize, the addition rule lets us find the probability of either one event or another occurring. For mutually exclusive events, we simply add the individual probabilities. For events that can occur together, we need to subtract the probability of their intersection to avoid counting it twice. Understanding the addition rule is essential for calculating probabilities in many real-world scenarios. The multiplication rule is a fundamental concept in probability theory for finding the probability of two events occurring together. When we talk about independent events, we mean events where the outcome of one does not affect the probability of the other occurring. Let's use a simple coin flip as our example. When flipping a fair coin, the probability of getting heads is 1/2, and the probability of getting tails is also 1/2. Now, let's consider consecutive coin flips. What's the probability of getting heads on the first flip and heads on the second flip? Since each flip is independent, we multiply the individual probabilities. A probability tree diagram helps us visualize this process. Starting from the left, each branch represents a possible outcome with its probability. To find the probability of a specific path, we multiply the probabilities along each branch. This table shows how the multiplication rule applies to multiple coin flips. As we increase the number of flips, the probability of getting at least one head increases, approaching 1 as the number of flips becomes large. The multiplication rule applies to any sequence of independent events, not just coin flips. This probability tree shows how to calculate the joint probability for drawing colored balls. For each complete path, we multiply the probabilities along the branches. Remember, for independent events, the probability of both events occurring is simply the product of their individual probabilities. In this section, we'll explore conditional probability and Bayes' rule, two powerful concepts in probability theory. Let's start with conditional probability. This is the probability of an event occurring, given that another event has already occurred. We can visualize conditional probability using Venn diagrams with overlapping circles. Each circle represents an event in our sample space. The formula for conditional probability is written as P of A given B, which equals the probability of A and B occurring together, divided by the probability of B. Here's a visual representation of conditional probability. It shows how we calculate the likelihood of one event based on the occurrence of a previous event. Let's look at a specific example using a Venn diagram. Here we have two events, A and B, with some overlap. The numbers represent the count of outcomes in each region. We can calculate various probabilities, including conditional ones like PAB. Now, let's explore Bayes' rule. This powerful formula allows us to update our probabilities when we receive new evidence or information. Bayes' rule can be visualized as a flowchart. We start with a prior probability, multiply it by the likelihood, and divide by the evidence to get our posterior probability. This allows us to update our beliefs based on new information. Here's a practical example where we can apply conditional probability and Bayes' rule. In this hurdle jumping scenario, we need to find the probability of hitting exactly one hurdle. This involves calculating conditional probabilities for different sequences of events. To summarize our key points, conditional probability is the probability of an event given that another has occurred, expressed as PAB equals PA and B divided by P of B. Bayes' rule allows us to update probabilities based on new evidence. It's expressed as PAB equals P of BA times P of A divided by PB. In statistics, measures of variability help us understand how spread out our data is. There are several important measures of variability, including range, variance, standard deviation, and intercore range. Variance is one of the most important measures of variability. It quantifies the average squared deviation of data points from the mean. The formula for population variance is the sum of squared differences from the mean divided by the number of observations. Let's consider a simple dataset of 6 numbers, 4, 8, 15, 16, 23, and 42. The mean of this dataset is 18. To calculate variance, we first find the deviation of each value from the mean, then square those deviations, sum them up, and divide by the number of observations. Standard deviation is simply the square root of the variance. It's often preferred because it's in the same units as the original data. The standard deviation is particularly important in the normal distribution, also known as the bell curve. It tells us how much the data spreads around the mean. The empirical rule, also known as the 68-95-99.7 rule, tells us that in a normal distribution, approximately 68% of data falls within one standard deviation of the mean. About 95% falls within 2 standard deviations, and about 99.7% falls within 3 standard deviations. Think of standard deviation as a ruler that measures the spread of data. A smaller standard deviation means the data points are clustered close to the mean. A larger standard deviation indicates the data is more spread out. When comparing datasets, the standard deviation helps us understand their relative variability. Measures of variability are essential in many fields. They help in quality control, risk assessment, scientific research, and educational assessment. By quantifying the spread of data, variance and standard deviation help us make informed decisions and draw meaningful conclusions from our data. Random sampling is a fundamental technique in statistics where we select a subset of individuals from a larger population. Why is random sampling so important in statistics? There are several key reasons. First, it ensures our sample is representative of the population we're studying. Second, it reduces bias that might occur with other sampling methods. Third, it allows us to make valid statistical inferences about the population. Finally, random sampling forms the foundation for confidence intervals and hypothesis testing. Let's visualize how random sampling works. Here we have a population of 15 individuals, each with an equal chance of being selected for our sample. In simple random sampling, each individual has an equal chance of being selected, and all possible samples of the same size have an equal chance of being chosen. Here's another visualization of the random sampling process. We start with our complete population and randomly select individuals to create our sample. The random sampling process follows these steps. There are several types of random sampling methods used in statistics. Simple random sampling gives every individual an equal chance of selection. Stratified sampling divides the population into groups called strata, then samples from each. Cluster sampling divides the population into clusters and selects entire clusters at random. Systematic sampling selects every kth individual after a random starting point. Random sampling has many important applications in the real world. The ultimate goal of random sampling is to allow us to make inferences about the entire population based on data from our sample. Remember, random sampling is the foundation of statistical inference, allowing us to draw valid conclusions about populations from our samples. Confidence intervals are a critical tool in statistical inference. A confidence interval provides a range of values within which the true population parameter is likely to fall, with a specified level of confidence. Statistical inference allows us to draw conclusions about a population based on sample data. When we calculate a sample mean, we're using it to estimate the true population mean. A confidence interval consists of 3 key components: the point estimate, which is typically the sample mean, a critical value based on our desired confidence level, and the margin of error, which accounts for variation in our sample. Let's visualize a 95% confidence interval. In this bell curve, we're capturing the central 95% of the sampling distribution, leaving 2.5% in each tail. What does 95% confidence actually mean? It means that if we took many samples and calculated intervals for each one, about 95% of those intervals would contain the true population parameter. The mathematical formula for a confidence interval is the sample mean plus or minus the critical value multiplied by the standard error. Each component plays a specific role in determining the width of our interval. Researchers commonly use different confidence levels. A 90% confidence interval is narrower but less certain. 95% confidence is the standard in many fields, and a 99% confidence interval is wider but provides more certainty. Let's work through a practical example. If our sample mean is 75 with a standard error of 3, we can calculate a 95% confidence interval. The critical z-value for 95% confidence is approximately 1.96. Multiplying this by our standard error gives us a margin of error of 5.88. So our 95% confidence interval ranges from 69.12 to 80.88. This means we are 95% confident that the true population mean falls within this range. To summarize, confidence intervals help us quantify uncertainty in our estimates. Wider intervals provide more confidence but less precision, while narrower intervals offer less confidence but more precision. And importantly, larger sample sizes help reduce the width of our confidence intervals. P-values are a fundamental concept in statistical inference. A p-value measures the strength of evidence against the null hypothesis. The null hypothesis, often denoted as H*, typically represents a claim of no effect or no difference. Here's a visual representation of a p-value. It's the probability of observing a result as extreme or more extreme than what we observed, assuming the null hypothesis is true. Let's interpret what different p-values mean. A small p-value, typically less than 0.5, suggests strong evidence against the null hypothesis. Conversely, a larger p-value indicates insufficient evidence to reject the null hypothesis. It's important to note that a p-value is not the probability that the null hypothesis is true. This is a common misconception. This graph shows the concept of statistical significance. The vertical line represents the threshold, typically set at 0.05 or 5%. When our observed result falls beyond this threshold, we consider the result statistically significant. Here are the steps in hypothesis testing. We start with data, state our hypotheses, select and calculate a test statistic, and then make a statistical decision based on the p-value. When making decisions with p-values, we typically follow these rules. If the p-value is less than 0.05, we reject the null hypothesis. If the p-value is 0.05 or greater, we fail to reject the null hypothesis. Note that we never accept the null hypothesis. We can only fail to reject it. Here's an example of a p-value calculation. In this case, we have a normal distribution with a mean of 10 and a standard deviation of 1.5. The p-value for observing a value of 13 or greater is 0.023, which is less than 0.05. Since the p-value is less than 0.05, we would reject the null hypothesis in this scenario. This image illustrates how the p-value relates to the observed result. When the observed result falls in the green shaded area, it indicates statistical significance beyond the 95% threshold. In summary, p-values provide a standardized way to evaluate evidence against the null hypothesis in statistical testing. In future videos, we'll explore more advanced statistical concepts and methods for analyzing complex data.